Ladies and gentlemen, welcome to this next episode of Fast Track Insights. Today we're going to discuss the world of quantum. My name is Nienke Dijkstra and I'm the Director of SME Startups and Scale-Ups at TNO. Before we start going into depth on the team, just some practicalities. We love this episode to be really interactive, so please join us by putting your questions or your remarks in the button within your screen. We would love to answer them up in the next hour. I brought a great lineup for you today, and we're going to discuss quantum. As we could have read in the national technology strategy that has just came out 2 weeks ago, we can see that quantum is actually in the top 10. So it needs a little bit of extra attention and it will get extra attention. So therefore, we have a really nice program today. And we're going to start a little bit light, although light on the quantum field, I'm not too sure what that means. But on the left of me, there's Henk, and Henk is my colleague of TNO. And next to my colleague of TNO, he's also involved in QTech. And QTech is the Knowledge and Research Institute collaboration between the TU in Delft and TNO. Henk is going to tell us all about the basic principles of quantum technology. Then on my right, we have another colleague, and she's specialized in quantum sensing. And she's also involved as the head of quantum sensing applications at Quantum Delta NL, which is the ecosystem around the team of quantum. And she's going to tell us all about the quantum sensing and the state of tech. Then we also have invited our partner InvestNL, Gert-Jan, director of the Deep Tech Fund, and he's going to tell us how we could join the revolution of quantum, what needs to be done in the investing landscape, and how the landscape looks like. So let's start. I think we are all ready. And please do not forget to ask us any question you have on the topic. Then Henk, before we dive into the qubit technology, the cats, I already seen some, can you tell us a little bit on why quantum is so promising and complex and where we are at this very moment? Can you tell us a little bit about the history?
Yeah, sure. I'd love to do that. So I will tell you a little bit an introduction into what we mean with quantum technology and with quantum physics. So quantum physics is basically the theory that was devised about 100 years ago in order to explain observations that were done at that time on very small particles. And these observations were not in line with the existing theories. So at that point there was a need for a new theory called quantum mechanics. And it's about special things like superposition and entanglement that was observed with these particles. So that's basically, let's say, the physical theory that is at the core of quantum technology. Now, with quantum devices, we mean very small devices that we design and really fabricate that exhibit some of these quantum properties, namely superposition and entanglement. For example, you can make qubits on a very small device. Now, when you integrate such devices in a greater system, then we are talking about real quantum systems, for example, a full-stack quantum computer system. So that's a little bit an introduction in what we mean with quantum physics and quantum technology. So quantum technology already started, let's say, in the 50s and the 60s of the last century. So at that point in time, people were already able to make devices that followed some of the rules of quantum physics. And typical examples of these devices are, for example, transistors and lasers. And these are really at the core of, let's say, the technique that we see in our daily life around us, in telephones, in cameras, in televisions, for example. That's the first quantum revolution. At the moment, we are in the so-called second quantum revolution, and that is really about really controlling the very small particles to an even greater extent than before. And if we are able to do so, then we may develop technology that is able to do calculations faster, to store more data, to have more accurate sensor, more sensitive sensors, and so on. So that's really the promise of the second quantum revolution. quantum physics is a physics theory that was already developed 100 years ago, as I mentioned. So here you see a brief timeline. So it was already in 1999 when first people discovered very small particles that behave differently from existing theories. And in the subsequent years following after that, many more discoveries were done and written down in what we call now quantum physics. And in the 60s, 70s, and 80s, many experiments were done, to investigate quantum physics. But also, what was needed for that, many new technologies and techniques were developed in order to do those experiments. And all these techniques and methods are very important for the quantum technology that we are working on nowadays. And in the end, this also led to the rewards by 2 Nobel Prizes for very famous physicists. So I will introduce briefly a few concepts of quantum physics. What is very special about quantum physics is that physical properties like energy, but for example also the mass or momentum, is quantized. So meaning that it cannot attain any value. It is really given by a specific number of values. So when you think about, for example, a planet that orbits a star, it could be in any orbit, it could have any energy. But when you think about an electron circling around an atom, it cannot have any orbit. It's only in specific orbits with specific energies. So that's quantization. Now, another very important principle is Heisenberg's uncertainty principle. And this is about the fundamental limits to the accuracy with which we can measure certain physical properties like momentum and position. And it's depicted in this picture over here. For example, when you want to measure the position and the speed of an electron, which is moving, then you have to do an observation. And that's usually done, for example, by shining light on it, emitting a photon. Now, when that is done, the electron will reflect the photon to the camera or to your eye, so you can observe where the electron was. But what happens in the meantime is when the photon hits the electron, then also the speed is changed. So meaning you cannot, to a very precise extent, measure at the same time the momentum and the speed. And this is a fundamental limit that cannot be resolved by better measuring techniques. So this is...
Sorry.
Yeah.
And Henk, is this from the first revolution? So is this already dated from a long time ago, this principle?
This date is already from a very long time ago, indeed.
Okay.
Other very interesting principle is the so-called wave-particle duality. So in order to really understand the all properties of a quantum system, we really need to use both the concepts of particles and waves that also occur in classical physics. But in quantum physics, you need to use both concepts to really understand the quantum state. So what you see in this picture, for example, when you would shine light, so a wave-like phenomenon, on a wall with 2 splits, then the wave splits up in 2 waves, and afterwards it can combine again. And then you can have a constructive and a destructive interference. So when the interference is constructive, then you will see the light over there on the screen. And when it is destructive, then you will see no light. So you will see this pattern that you see over there. And the interesting thing with quantum physics is that this is also basically happening for particles. So particles mostly are not considered by people as waves, but they do have wave-like behavior. Namely, when you would shoot particles that have quantum physical behavior to this wall, then the probability of finding a particle at a certain position is also described by a wave-like phenomenon. Meaning that also the particles that go through the wall may end up at very specific positions, namely given by the interference in a constructive or in a destructive way. That is called wave-particle duality. And what we saw in the previous picture is that this particle has a probability of being at some places at the same time. And that is called superposition. So in principle, particles can be at the same time as long as you do not observe them. At the point when you want to observe particles, then you will find them either in this place or in the other place with a certain probability. And this probability can be predicted by quantum physics. But the only way to measure that is not by only doing one observation. You should do many, many observations and then do counts to see what the probability is where to find such a particle. So that's called quantum superposition and quantum measurement. When we have two quantum physical particles, in this picture depicted as cats, there are different states in which they can occur. So in the first state, it's the so-called not entangled state, meaning that the white cat that can be asleep or can be awake is completely separate from the black cat that can be asleep and can be awake. So when doing a measurement on the white cat, at some point you will observe him being asleep, but that doesn't say anything about the black cat. That's for the not entangled state. But the very special thing about quantum physics is that there is also something like quantum entanglement. And that's basically depicted in the picture underneath. So here we have a superposition of a sleeping cat, white or black, or a cat that is awake, white or black. And now the special thing is, when you do a measurement on the white cat, then you will observe, for example, that he's asleep, but then you immediately know, no matter how far the cats are from each other, if the other cat is also sleeping or awake. So that is called quantum entanglement.
And what mechanism is driving that? Is that known?
Well, that's very hard to explain.
For another hour. Okay.
Yeah.
Next episode.
Yeah. So these concepts of quantum superposition and quantum entanglement are basically brought together in so-called quantum bits, and a very natural candidate for a quantum bit to be implemented in reality is, for example, an electron. So an electron that circles around atomic nuclei. These are very small particles that do have a quantum physical property called spin. And spin is something like the rotation of the electron around its own axis. And the rotation can be in one direction or in the other direction, meaning that the spin is pointing upward or downward. And now it comes that this electron can be in a superposition of spin up and spin down. So here we have a quantum bit that is in two positions at the same time, meaning that it can store more information than a conventional bit. A conventional bit can only be in one position at the same time. And also when you combine these quantum bits together via entanglement, then we also have the ability to do much faster calculations, for example. Now, an electron is one example of a quantum bit, but there are also other examples how to implement quantum bits in reality. Another interesting thing is, for example, superconducting qubits. That is used already quite a lot in quantum computing systems that can be accessed by the cloud for everyone, actually. And another very interesting quantum bit system is the so-called NV center endowment. So a nitrogen vacancy endowment leads to a specific configuration of electrons that can easily be accessed by laser light shining on it. So in that way, it can be controlled in a very convenient way. There are many more quantum bits that people are working on, but let's go on.
Hey, and Henk, this sounds quite, even for me, quite simple with the cats, and I understand everything. But listening to you, I think there are still some challenges ahead, right? So what are the main challenges in developing better quantum bits? So there are still already a couple around, you mentioned. But could you maybe elaborate what the challenges are and how could we speed things up?
Yeah, so what is very difficult about quantum bits is how are we going to develop quantum bits and place them in a location where they can keep their information. And that is a property called coherence or decoherence. So this information may get lost in an unwanted way when the quantum bit interacts with the environment when you don't want to. Well, people are working hard on trying to solve that, but on the other hand, if you want to manipulate the quantum bit, you also need to have interaction. And this interaction should be very perfect, because otherwise you are not going to store the information that you want to store. And this is very important. Let's say the coherence and also the fidelity of the operations is very important. It should be very much better in order to reach quantum computers that are really capable of solving actual problems.
Yeah.
Another other difficulty is, for example, scaling up using many more quantum bits. So also related to quantum computing, for example, if you want to do useful quantum computations, then you need many more quantum bits. But when you look at the very simple demonstrators that we have nowadays, for example, when you look at the cabling that is needed to only, let's say, drive a couple of qubits, that is already huge. Yeah. But imagine when you have to scale up to thousands or maybe millions of qubits, that is not going to work in the way we are doing it right now. So people really need to make completely new designs and new techniques to, to drive these qubit systems.
And to make it more sustainable, I guess.
Yeah.
Okay.
Yeah, so basically, just to recap, so the most important quantum mechanical principles that is, let's say, at the core of all quantum technology is what we call quantum superposition and quantum entanglement. And this is used in all quantum technology, ranging from quantum computing to quantum communication and also to quantum sensing.
Mm-hmm. The first questions are coming in. So let me ask you the first one. What is the best qubit technology that we have at this very moment?
Interesting question, but not very easy to answer, I guess. So there are different technologies that we are working on, and it really also depends on the application. So when you look, for example, at quantum computing, the qubit technology that is used quite a lot nowadays is the so-called superconducting qubit transmons. And these are really used by, for example, IBM, that has computers that are accessible by the cloud to any one of us. But these qubits are very mature, so in that sense it's good. But for scaling up to, let's say, larger systems, this may be problematic because the qubits are relatively large. Another technology that I mentioned is electrons. So electrons confined in solid states are much smaller scaled, so that has a potential for scaling up. But it's a technology that is not that mature yet. So there's still a lot of research needs to be done for that. And these are just examples for quantum computing. For example, for quantum sensing, people are usually using NV centers. So it's a bit dependent also on the application, as I mentioned. Yeah.
Okay, so maybe that is also a really nice bridge to our next topic. Because we've learned that it looks simple with the cats. It already took us more than 100 years to get where we are. But I think there are still already some promising applications. So let's move on to a little bit more into the technology, a little bit more in depth. And for today's episode, we've chosen the subject of quantum sensing. Clara, maybe you can explain a little bit more about the different fields and how quantum sensing, what is already possible, and about the work that you were doing.
Yes, sure. One thing that I would like to start saying is repeating actually something that Hank said. Why are we now here talking about this? It's not only because we understand quantum mechanics so well, but because we developed the technology to control those bits that Hank mentioned. So we are now able to put information on them, to use entanglement and superposition to really encode information. And this opens application areas. So imagine that you have one of these bits, you encode your information, and you send it from Amsterdam to Rotterdam. Then you have quantum communication. You are communicating using these bits. And the fact that you have entanglement and superposition give you some advantages. Henk already mentioned computing. In computing, what you do is you encode the information and perform operations on these bits. And that allows you to do to solve mathematical problems that are normally not accessible with normal bits. And finally, what you can also do is you can encode information in one of these bits, let it interact with the environment, and see what the environment does to that information. And that is the basis of quantum sensing. So in the following minutes, what I'm going to do is to try to explain you what is a quantum sensor and give you a flavor of the technology readiness level of this application area.
Perfect.
So let's start with the basics. What is a sensor? So we can say that a sensor is a device, is a little machine that translates a stimuli, like for instance the light, the sound, the temperature, into an electric signal that is then going to be processed by a computer. This is simple. You have stimulus, your sensor, and electric signal. If you start thinking in this way, you're going to realize that sensors are everywhere. So you have thermometers in your house, you have CO2 detectors, we have this microphone. In your phone, there are at least 20 or 30 seconds sensors. Sensors are everywhere. And if you pay attention, you're going to start seeing them everywhere. And this is one of the interesting things of thinking about sensors and new kinds of sensors, is because their ubiquity. Any new sensor with new performance has the potential to have a big impact. In particular, what we are talking today are quantum sensors. So what are quantum sensors? Quantum sensors are a particular type of sensors where this translation process between the stimuli and your electric signal happens when you use these bits that Henk introduced, when you use them in a very controlled way. So for instance, when you encode the information, you let it evolve, and after you read out the final state, and you see, and then you translate that to an electric signal. You can use the state of the qubit or the coherence, or you can use entanglement and superposition. So this is still very abstract, and we had been talking about qubits and qubits this and qubits that, but what can be qubits? What, like Henk mentioned it already, but I wanted to give you an impression of what is possible in the world of to use as sensors. What things can you use? Because in general, you can separate the qubits or the systems that you can use as sensors, as quantum sensors, in two large categories. You have gases, clouds of gases, and you have solid state. This is from you pretty much have an idea of that they are very different in nature. In the, let's say in the gas family, you have single atoms, single ions, you have clouds, room temperature and cold clouds. And in the solid states, well, it's a complete universe. You have defects, for instance, the envy centers that Henk mentioned, defects on solids. You have the superconducting circuits, squeeze, quantum dots, and you have other systems like optomechanical systems or even light. One important thing is I'm putting here like a list of possible things that you can use as sensors, and there is a lot of development to control better, with more fidelity, all these kind of systems. And one important thing to understand is that all this work that is done is usable for sensing, and then for computing, and then for communications. So, yes?
Yeah, sorry. One question is coming up, and I think it fits the story where you are at right now, and maybe a little bit of Henk's. Does changing one qubit, which understand changes and intertangled other qubits, require a lot of energy? That's the question. Is this a potential for long-range, high-speed data communication?
Okay, so these are multiple questions.
Yeah.
In practice, changing one qubit for other is not so easy, because the way that you address the qubit, or like how you, let's say you are like a trainer, how you train these qubits is very different. Like to atoms, you speak in a way that is not the same that you speak to photons. Mm-hmm. So you will need, for instance, different lasers, different detectors. That is one thing. This is related to changing one qubit for the other. The other point is, can you transmit information? Yes, of course, because you can encode, you can use light or the fundamental particle of light that is called a photon, you can use it as a qubit. So you can encode information in a single photon, in a single particle of light, and send it through, for instance, your optical fiber.
So this is what we in the future will call quantum internet.
This is the base for quantum internet and quantum communications.
And it requires a lot of energy, because that was also part of the question.
Yes.
Okay. The easy answer, yeah.
Okay, well, going back to sensors, so we have this huge landscape of possible systems that can be used for sensing. And what makes things even more broad is that each of them are sensitive to different things. You have some systems that, for instance, are sensitive to magnetic fields, to electric fields, to accelerations or rotations, to pressure, to force. So it is really a world of possibilities. In the table that we are showing right now, what you can see is the technology readiness level of some of those sensors. You have already, you have many possibilities that are like demonstrated in laboratories, in academic research labs around the world, but you also have systems that are commercially available. So in the following minutes, what I'm going to do is to give you 3 examples of different sensors with different applications that are at different stages of development. The first one is based on a cold cloud of atoms. Because this is a very physics-heavy webinar, let's go to yet another topic that the physicists are very fond of, gravity. Gravity is this force that pushes towards the center of the Earth. This is the force that attracts objects that have mass. And when you are able to measure the gravity of a place very precisely, you actually learn a lot about the components from here to the center of the Earth of that place. You can see if there is mostly ground, if there is water, if there is gases, and therefore the gravimeters or machines that measure gravity are so important. Here we have an example of a gravimeter. This is a commercial system by a company called Excel, formerly Mukwang's. This gravimeter is able to measure gravity with a quite good accuracy and precision, comparable to classical gravimeters. But what it makes it very interesting is that this is a portable system. It's smaller, it's more compact, and actually have a lower power consumption. Which is something that you normally not associate. Like if you think quantum high-tech, you are imagining, well, also the price. The price can be lower than classical systems. And it can operate for many, many years. So using this kind of system, for instance, they made maps of the gravity around the Mount Etna in winter. They could measure during all winter. Before that was not possible because the classical gravimeters will need so much energy. And this is a location that is isolated during winter, so you could not provide this energy. But with these systems, it's possible.
And why do we want to measure the gravity fields?
So for instance, around Mount Etna, you learn how the magma is moving. But you can also learn where is water or where are other minerals that can be interesting. Okay, a second example is also based on atoms, but in this case, the atoms are actually at room temperature. So optically pumped magnetometers are a type of magnetometer. This is actually, you can buy it commercially. It's like a small device. But what I wanted to show here was a particular application of these devices. And this application is for magnetoencephalograms. You know that in your brain, there are neurons, and they are transmitting energy via currents. And these currents produce magnetic fields. And you can, if you have a sensitive enough magnetometer, you can measure these magnetic fields. This is normally done with the squids, that are other type of quantum sensors. But squids need to be cooled down to incredibly low temperatures. So you have the sensor, you have the thing that cool it down, and then you need to have an isolation with the head of the patient. And as a result, your sensor is very far from your brain. And then you get information, but you don't have so much spatial resolution because you are so far. With these optical pump magnetometers, they are at room temperature. So they operate at room temperature, and while they have like a little bit less sensitivity, you can get closer. So you can make higher resolution images. And
so better diagnostics within the medical industry.
yes, and there is also something important. Not only you get more information, but this is accessible to a higher variety of patients. Because if you see the picture for, this is actually from a research from the UK, the standard magnetoencephalograms are very massive machines, and they are made for a size of head.
Yeah.
So if your head fits in the machine, you are good. But if your head is like small, for instance, like a children, the machine will not work for you. These systems allowed to put the magnetometers in helmets that can be used for the different variety of patients.
So they have real advantages in comparison to, let's say, other products you can buy right now.
Yes.
Yeah.
Yeah.
So that's important also for market adoption.
Yes, of course.
Is this commercially available?
Well, the single magnetometer, there is, like let's say, one point on that helmet is already a product. You can buy those for many other applications. This is still in development, this helmet idea. Okay? And then the third example is a solid state example. It's based on MV centers. Actually, Hank briefly introduced them. These are defects on diamond. So diamond is actually a material composed by carbon, and when this material is being made and being formed, many bad things can happen. These MV centers come from the result of one carbon atom actually disappearing and one of his neighbors being replaced by a nitrogen, so nitrogen vacancy in a diamond lattice. So that is a single atom. This is the single nitrogen and the space next to it, and we can address it, so we can talk to it, and we can read its state. So what we have here is a sensor that is the size of a single atom. So what we can do, for instance, is to, and it's, by the way, sensitive to magnetic fields, again, and to temperatures. So what we can do is we can put this single defect in a position, measure the magnetic field, and move to a next position in a sample. And we can image magnetic field distributions or even currents with a huge resolution, around 50 nanometers. So there is an image of our instrument in TNO, and a picture of the instrument, and the kind of images that we can produce. And it's important now to say that, like, this is our instrument, but while we were developing, there are also 2 or 3 companies that they are selling these kind of instruments commercially.
And what are the end users then doing with these kind of pictures? Because I understand your story, but I think it's also interesting to learn what the end users, so where is it used for? What is the real application? So
this is a very interesting question, and it's also at the core of what we are trying to do at TNO. So we know, and we are extremely enthusiastic about the technology, and we know the potential, and then the people that we normally work with for other projects inside, like TNO, our customers, they don't know. So we are trying to shorten that bridge. So what we are trying to tell people is come and visit and see what we can do for you.
Yeah, and what is really nice, because there was one question, it was already a couple of minutes ago, but the question was, to what extent is TNO involved or designated to create value and spin-offs with this science and acquired knowledge? I hear a certain overlap with the more fundamental studies and institutes such as CERN, DIFER, but I think you already answered the question. Thank you for putting it out there, but I think you just answered it. But maybe if you can elaborate.
I actually have a slide about it. So what
I should have known that.
What we are trying to do in TNO is to use all the know-how that we have in our work for instance, for space, for semicon, for defense, in other areas, and get that knowledge and use it to accelerate the industrialization of quantum sensors. And as I described before, what we see is that the technology is very well advanced, and there are many applications, and we are trying to really push these applications to the market. So what we came with this idea of a test bed facility. This is a facility where we have technology that was developed either in TNO or by the universities or commercially acquired. And then what we invite is people that want to learn more and who want to see the hardware to come, see how it works, see the possibilities, and make questions and come with use cases.
Are the knowledge institutes willing to share all that knowledge? Because I can imagine that it's kind of, it brings up a barrier, you know, if you want to protect perhaps your knowledge.
Yeah, of course, like the technology that is there is being protected by IP and things like that. Yeah. But the moment that we are right now is developing use cases. So depending on who comes and which question, then we also establish a collaboration. Okay, who owns which IP and things like that. Exactly. But this is more in the developing of the use case.
Yeah.
Okay.
Yeah.
So our testbed facility actually started in 2022, and we are working more and more towards dedicating most of our time to use case testing. To give you an idea, we work mostly on, we work pretty much basically only on systems based on these MV centers that I introduced before. And we have these scanning probe microscopes, the ones that allow to make the image. But we also have high sensitive magnetometers, like the highest possible sensitivity for this kind of system, that we are exploring their use in navigation. And we also have microscopes that allow to make fast images of magnetic fields and currents. And then the invitation for the people that are seeing is if they are curious, they can come again, look at the technology, and see how they can be used in their own business. Yeah.
Wow. Impressive.
Really impressive, and also already, I think, really applicable, right? Yeah. So we learned that you are actually searching for new applications, so we can improve also our tests. Our test beds and the way we are moving forward. But I'm quite curious, what are the things that you are currently working on? So what is your next big thing? You have an important role at Quantum Delta NL, but also at TNO. So please, a little jump into the future. What is the next big thing for you? What are you working on?
So, okay, I have two hats now. So in the TNO domain, we're really curious and excited about the applications of these scanning probe microscopes to characterize materials, to characterize currents inside those materials. And this is very, very strongly linked to our heritage on the semiconductor market. For the compound magnetometers, this idea of navigating with the magnetic fields is a little bit too complicated to explain right now, but it will allow you to navigate without the need of connecting to a satellite, like you do normally when you do GPS. So you are completely autonomous in your navigation. And this is very important when you don't have access, for instance, to the satellite. So let's say from our work in TNO, these are two things that we are very excited. And within Quantum Delta, what is interesting is that in our CAT3 program, that is says quantum sensing applications, this idea of the test bed facilities was, let's say, exported to a national level. So we have this test bed facility in TNO for sensors with MV centers, but there are another two facilities in the country, one for atomic clocks in Amsterdam and one for mechanical-based systems in Delft. So it's very interesting because now we have three types of technology. So if you come with a question that we cannot answer, we might be able to connect you to our colleagues and using other systems.
That sounds perfect. And I know we have a lot of viewers that are entrepreneurs. Which entrepreneurs could really benefit from quantum sensing? Who should send you the applications they are looking for?
So let's say the easiest, we are in a moment where we are actually still looking for more and more use cases where these technologies can be used. So if you are working on something and you have a problem that requires better sensors, this will be a good connection. On the other hand, we also see at the national level that even for the use cases that are demonstrated, that we know this technology will solve this problem, we still need companies that pick up this impulse and build the devices and build and commercialize the devices. So you can either link to this technology as a potential user or as an instrument manufacturer.
Perfect. And maybe this is also a really nice bridge towards Gert-Jan, because we have discussed the technology now quite a bit. But maybe in the phase of development where we are at, we also already mentioned a little bit, the ecosystem is also really important, and also the investing landscape. And I know InvestNL conducted research towards the quantum landscape and the investing. And I read, well, I think it came out maybe 2 days ago, the report on quantum, and they were discussing that it's actually, although we're moving towards spring, that it's actually a cold winter coming up for quantum. But maybe you can explain to us what the landscape looks like and where the challenges are.
I'm happy to. It will be, let's say, something completely different now.
Yeah.
After this impressive masterclass, so thank you both. I think you're referring to the IQM and Lakestar report, which came out recently. And they indeed talk about, and many other publications talk about the quantum winter. And I'm by nature a rather optimistic guy, so I don't believe it's a winter, but it's getting a little bit colder, that's for sure. So let's take you a little bit into the landscape of the ecosystem, but particularly here in the funding of quantum companies, quantum in general. And I think that the Netherlands is doing well. From an academic point of view, I think they're still on a certain type of quantum bits ahead in the world. And also maybe from a funding perspective. As you can see in this graph here, this table here, Netherlands is doing well in terms of a huge amount of capita per public spending on quantum. Even second in the world. However, if you look at on a more total scale, the Netherlands is dropping down to number 10. That makes sense because a lot of countries, for instance China, that is surpassing everyone with billions and billions of dollars a year spending in quantum. Back to the winter, or what I think, well, it's not that bad.
I feel something coming.
Yeah,
so I know there are a lot of investment managers also joining us today.
Absolutely. So my big thing is that I think we need a lot more of private investment in quantum. And I think there's every reason to it. I can come back to that later. But going back to some numbers, some stats, then it is true that from 2021 to 2022, the private investment in quantum dropped down with 25%. And last year, even with 50% on a global scale. So that's what I think refer to that winter. However, if you look a little bit deeper, in the US, it dropped down with 80%. And in Europe, it increased with 5% approximately. So it depends on where in the world you're looking at.
We're in a good state.
And I think another good news is that the public funding is still steady going on. And I think it's necessary. It provides all the starting entrepreneurs or academics who try to valorize their proposition towards the market. They find in the public funding a kind of a steady patient capital which enables, for instance, all the initiatives. So that's very important. But still, I think we definitely need more private investment in the whole quantum area.
So we need more deep tech funding, especially for quantum.
Yeah, I have a slide here where it gives you a little bit an idea of how the deep tech funding in Netherlands is organized or is actually stated right now. And not make it overcomplicated, but when you look to the x-axis, then at the left side, there are the funds that have one life stage of a company, for instance, in seed capital only. And when you go more to the right, you see more multi-stage funds. So that these are funds that are capable of funding more rounds, investment rounds within a company. And on the y-axis, you see, and that's an important thing, the lifespan of the fund itself. In traditional venture capital, you see that the fund period of a venture capital fund is 10 years. And that's not enough for quantum. But Henk refers to quantum computing. And I think you agree, Henk, that it still takes, well, maybe not decades, but much more than 10 years
Sure.
to get commercialized. And that's also from an investment perspective very important. It's very tough to invest with a traditional private venture capital fund when it exceeds the 10 years. So that's why we need some support from all kinds of funds. And going to sensing, as we learned from you, Clara, that there are already enough companies that are have commercially traction or even in revenue. That's more attractive from an investment point of view. If you look to this landscape, you see that there are also a couple of funds with a yellow star. These are the funds that are bigger than 200 million in fund size. And the one on the left is even not funded right now. So that leaves 3 funds in the Netherlands that have a fund size bigger than 200 million. And that's not a lot, to be honest. And the other truth is that these funds are not dedicated to quantum. So they all have a small part allocated to quantum of their fund, with exception of Quantum Delta participations. That's the only one in the Netherlands, at least, who is dedicated to quantum. And there's also now a big French fund, that's Quantination, that is doing great things in Europe, I think. So that's kind of good news. But this is a little bit insight in the venture capital landscape in the Netherlands, in Europe, and I hope it makes the term winter a little bit less cold.
Hey, and how, because, well, you have a yellow star with the Deep Tech Fund of InvestNL. How do you organize your due diligence? So if I'm an entrepreneur, one of the 2025, or I'm a company that wants to work with quantum sensing, what is important for them to know? How do you judge your investments?
Yeah, well, excellent question. It's a tough one, I guess, to go really into depth and make it very concrete, but I do an attempt. It depends on one of the areas of quantum. So quantum computing is rather different than quantum sensing. We learned that already. With quantum computer, the due diligence will be much more on technical due diligence. For instance, with our partner TNO, of course, but we go into depth on the real technological state of what the company is trying to bring towards the market. And there are other examples in the Netherlands, also within communication, but certainly in sensing, but also in controlling. So the controlling is a part of quantum computing. Where companies actually are making money. They will make money. They are in revenue, and they're scaling up actually, and that will actually. I think we are going back to a little bit more normal due diligence. So we also do validation with customers or potential customers. We investigate the market, and so I think the maturity of a big part of quantum is getting such mature that it's feasible for venture capital.
That's great to hear.
Yeah, absolutely.
Yeah. So that on the funding part, but we already touched a little bit upon the ecosystem.
Yeah.
What would you say is the biggest challenge in the Dutch or maybe European ecosystem?
Yeah, we learned that from our research in October last year. And there are 2 major subjects. One is funding, maybe obviously, and the other one is around facilities. And let me take another slide here, because there's also very good news. We are very happy with the fact that Quantum Delta is in the Netherlands. An organization that is really there for the quantum ecosystem. And I was mentioning facilities, that's the second part. What we learned from our interviews is that companies suffer, especially not for the quality of the facilities, but more the availability. When you have lots of shared facilities, you need time to reconfigure machinery, and well, those kind of things are a hurdle to make use of full capacity of all these facilities. But Quantum Delta, this is actually one of the themes of Quantum Delta. But Clara, since you also your other hat is the quantum delta hat. Maybe you can help me out a little bit, but you have a lot of lines where quantum delta is focusing on, besides quantum delta participations.
Yeah, so actually, I think the Netherlands should be very proud of this initiative. This is an organization and an ecosystem. And so what you see in this little diagram is that the organization not only focuses on technology development. The technology development is done in this CAT1 for computing, CAT2 for network and communications, and CAT3 for quantum sensing. So there is this technology part, but there is also a lot of effort that is being put on the ecosystems, on creating the ecosystem, on training the people, like doing fundamental research, but also supporting industry and supporting SMEs and startups. And even we have a complete program evaluating how to increase the societal impact of all the things that we are doing around quantum. And there is, of course, this huge support on providing facilities like the clean rooms.
Yeah. And I think that the fact that quantum delta participation is a very early stage,
yep.
That gives the ability from academics, for instance, to really start up in the Netherlands. You have the ability there. And well, that makes a good, complete portfolio of
resources.
Yeah, exactly.
Yep. Yeah, available resources. Well, that brings us maybe to the next subject, like how to collaborate and accelerate. Maybe we triggered you a little bit on certain fields, possibilities, and funding options. Quantum technology at TNO is growing. It's maybe even the fastest growing department we have. Already more than 150 colleagues are working on this technology and on the facility. Clara, I already have one visitor for you who would like to visit the testbed facility, so we make sure we refer that correctly. But what can you do? I think at TNO Fast Track, and TNO Fast Track is the platform for SME startups and scale-ups, we find it really important to also take the next step. So if you want to know anything, maybe reach out to Gert-Jan, Quantum Delta NL, or visit the testbed at Clara. Please reach out to us. You can find us at tno.nl/fasttrack, and we will connect you to the ecosystem. But we also think is really important. Of course, this is a lot of, let's say, knowledge transfer that we are doing, and of course we do it in an interactive way. And I thank you already very much for all the questions coming in, so keep on posting them because we still have a couple of minutes to go. But we also find it important that if you want to know more, that we as TNO also offer you a really concrete and a really practical follow-up. Therefore, we designed the Quantum Quick Scan. So if you would like to learn more and go more into depth what it means for you, please feel free and feel welcome to let us know, and we will set it up. Let me check, because let me have a look at the questions that came in.
You have a lot of questions.
Yeah, that's perfect. Yeah, this is a difficult one, but maybe it's nice to go back to you, Henk. How far along is quantum computing? Is it already commercially viable?
No, I don't think so. With the current quality of qubits, you can do so-called NISQ computing, and that basically means that you are using, let's say, very noisy qubits that you can use to a certain extent. So you can run very short algorithms, which require only a couple of qubit operations. But the problem is when you want to solve real-world problems with a quantum computer, then you need to do very lengthy calculations, meaning that the qubits should be very coherent, and that is one of the big problems with the qubits that we have right now. They lose their quantum information in due of time. So at the moment, that's not possible.
Can I, with the very risk of going against the scientist, with a little nuance, I think that with the capabilities of the current quantum computer, in an academic world, there's you can talk about some commercialization, because the 64 by 64 quantum bits are bought by in an academic world, isn't it? So you have a kind of it's not the whole changing the whole world with quantum computing, but the first quantum computers processors are actually operational.
Sure. And also accessible via the cloud, for example, for IBM and other institutes, indeed. So these are really working quantum computers.
Very early stage commercialization.
Very early stage indeed, yeah.
And would it then be fair to say, if you want to go into that direction, that it's advised to step in at this very moment, or should you step in when it's a little bit further away in development, and maybe not only for quantum computing, but also for the quantum sensing? Or would you say, no, this is early days, I think, for all of the areas that we are discussing, one's a little bit more than the other ones, but what would you advise to entrepreneurs that are just starting, or maybe even corporate organizations that think, hey, the geolocating or the GPS, that sounds interesting. Is that the right timing now to step up?
I think it's very difficult to answer this question for, let's say, the general group that you mentioned.
Yeah.
If you want to be involved in the development, if you want to have IP and a position on the development of the knowledge, then this is a good moment.
Yeah.
If this is the core of your business. If you want to be, let's say, an end user of one of these devices, and you are not so interested in the development, I think that it's still important to be involved, to learn and to know what is possible, but it's maybe not the moment to put all your horses in,
I think I understand, and that it's really clear, because you already mentioned that the direction is still being chosen. So if you step in this very moment, you still have some, how do you say that?
You can steer.
You can steer.
Yep.
Thanks so much. Well, I think we came almost to the end of this webinar. I think we've learned quite a lot. At least I did.
Too.
But I think it's really nice to have the investment and the business perspective versus the technology perspective. So we learned a lot about the basic principles. It took us more than 100 years to get where we are. It looks really simple with the cats, but it's actually not. So there's still work to do. But I think the last question or the last answer, maybe step in, this is not a really bad time to actually step in. Then we talked a little bit more about the state of tech, quantum sensing. Well, I have the first interest parties that want to join you on the testbed. So we will refer them to you. A lot is already possible, and maybe to highlight also your question, come with your ideas, your concepts, new applications, and let's see what can be done. Then Gert-Jan, more private investment is needed to stay ahead. I think the good news was that we are actually ahead.
Doing well.
Doing really, really, really well, but let's keep it that way. Yeah. I think that's also within, I already brought it up in the beginning, the national technology strategy. We want to keep it up. So if you're a private investor, please reach out and please keep on funding this domain. And we talked about how can you collaborate and how can you accelerate. You can find us at TNO, Quantum Delta NL, and also Invest NL. Well, thank you very much for listening, for sending in your questions. Also, Henk, Clara, Gert-Jan, thank you very much for your contribution. And maybe it's good to mention, because there was already a question, will the slides be made available? Of course, we will send you the whole webinar and the slide deck. So at your proposal. Maybe it's nice to mention that on the 28th of February we will be back. We will discuss the Green Deal, industrial transformation, and how can we make industry more sustainable. So maybe see you next time, and thank you for joining us today. Have a lovely day.
Thanks.
Have a nice day.